Well, welcome. My name is Drew Desker. I'm the director here at Kopernik Observatory. It's great to have a lovely crowd here this evening. We also want to welcome those watching on our live stream. I always do this, so I apologize to those who come here often. Who's here for the first time? All right, a good number of people. Okay, who here are members? Almost the other half, which is... So that other half actually knows something very important, very valuable, and it's the value of a Kopernik membership. Okay, we are a nonprofit 501c3. We don't get any real government support. We are not associated with a university or anything. So it's things like memberships, summer camps that we run, school things that ultimately help keep us solvent and keep us open. Part of a Kopernik membership, what a Kopernik membership does is it gives you access to over 350 other science centers. We belong to an association called the ASTC, Association of Science and Technology Centers. And with your Kopernik membership card, you can get into 350 of those other science centers. So you could go down to the Intrepid in New York City. You can go to the Franklin Institute down in Philly. You could go to Roberson or the Museum of Science and Technology up in Syracuse, all for free. And especially like if you're going down to the Intrepid or Franklin Institute, by the time you bring your family through, you've more than covered an adult or a family membership here at Kopernik. We do a number of things. Again, Friday nights we have an opportunity to sort of promote lifelong learning. It's great to see people of all hair colors here tonight, and. But again, we offer programs for young kids as young as 3 years old, our Kopernik kids. Right now we're running our summer camps. Right now we've got about 210 students that will come here at various times throughout the summer. And we just finished up a camp this afternoon, and we got another one starting next week. Are you coming next week? Oh, that's right. You're in my balloon camp. All right. And next week we're doing a high-altitude balloon project where these students are going to launch a payload on a helium-filled weather balloon that will leave right outside here hopefully on Wednesday morning, and will within about 2 hours reach 100,000 feet, about 20 miles high. We'll have cameras on there. We'll have some ham radio beacons. We're even doing some slow scan television to capture those images, and then we send out a recovery crew to go and snatch it out of the tree that will most likely land in. But again, we are all really about sort of planting seeds. One of the programs that we offer is a program called Kopernik, is called Girl Power Science, and it's for girls that are between 3rd and 8th grade. We're really trying to see more women in STEM careers. And we always have a female subject matter expert talk about the work that she does, that sort of, maps into the topic we happen to be covering that day or over those couple of days. And a few years ago, we had an astrophysicist from NASA talk about the work that she does using satellites to look at carbon dioxide levels and how it affects global warming. And then at the end of the presentation, our girls get to ask her questions because it's a Zoom kind of thing. And one girl asked, "How did you get interested in astrophysics?" And I loved her answer. She said, "Well, when I was in college, I was an English major, but my boyfriend was a physics major. And we'd go from observatory to observatory. I eventually dumped the boyfriend, but I kept the astronomy." She now has her PhD in astrophysics and works at NASA. So you never know where a seed's going to get planted. And that's really what we're all about. So hopefully we'll plant some seeds this evening. We're very fortunate to have on staff Jeremy Cartie. We call him our Livestream astronomer, but he actually started out as an intern and now is just an extraordinary educator for us. And he's done a lot of our Livestream observing sessions, and he might even talk a little bit about that. You'd be better to talk about it than me. And so we're going to.
Okay, so yep, mic's working good. So good evening, everyone. My name is Jeremy, and I'm a science educator here. And like Drew mentioned, I am the live stream astronomer for Kopernik as well. So you may have tuned in on some of our observing live streams in the past. I believe our last one was back in June, and we covered the Pinwheel Galaxy supernova. And we can even go back on the YouTube channel and see that pop right up here. We call those our NSLs, or Night Sky Lives. Just like NASA, we love acronyms, so we make use of them here. That was neat because we actually did capture that supernova event in our scope. Definitely not the best photo we have of it at Kopernik. If you want, go back on our Facebook page, and you'll find our Astro Society members' photograph from our 20-inch, which is very high quality. But we did capture it as a pseudo live view in our scope during that session. And we'll look forward to more observing live streams coming up. We always like to cover the Perseids, so that's coming up in August, and it will be a good year, assuming no clouds in our way. We'll have a nearly moonless night to work with during peak, so hopefully we can capture some live Perseids as well. So stay tuned for that, and of course every Friday night is also live streamed. You see after clicking on this live page, this is tonight's program, JWST First Year in Science, and it is streaming now. So we have some viewers on YouTube, and I'll wave to them at the camera here. All right, so let's jump into it. Here we go. And we'll full screen this if we can. Taking a moment. There it goes. All right, so JWST First Year in Science. So it has been out in space for longer, about a year and a half now. It launched on December 25th, 2021, which is kind of neat. During that time, it was flying out to Lagrange Point, and that's about 1 million miles away from the Earth. So it is pretty far out there, well beyond the orbit of the Moon. And after about 6 months or so, once it settled in and calibrated, it was starting to capture its first data. And there was a big event on July 12th last year that covered that. And we got to see the first images. This program won't focus on those first images, though. We already had a couple programs in the past that did. We're going to look at the more up-to-date imagery that came down roughly in the last 6 months, and get an idea of what it's working with. And in fact, this graphic is a sneak peek of that, including the background image. These are some of the top photos taken during this time, and maybe you recognize some of them. Some things will be familiar, other things will be otherworldly, certainly. So let's carry on the first year in science. And actually, I'm going to flip this light here. There we go. Because we're going to be looking at some images. You want those ones too? Yeah, I can do that. Yeah. That's it. Keep going to that. Yeah, we'll work with that for now, just because we are going to be very focused on images today. And I think, Drew, the camera's okay? You can see me all right? Okay, good. All right, so James Webb Space Telescope. Let's just talk about this phenomenal instrument that's out there a million miles away. If you're not familiar with what it looks like, first, these are the partners involved with its design and development. NASA led the program for JWST, and then ESA, the European Space Agency, and CSA, Canadian Space Agency, are partners on the program. So they all worked in tandem to design and build James Webb over decades. So let's take a look at the scope. There it is. So it's a pretty unique design, and that's in part because of how large they wanted this telescope to be. If you've seen Hubble in the past, in fact, for those that are here on site, you can look to that blue panel board on the wall and see pictures of Spitzer, Hubble, and Chandra. And you see they all take on this cylindrical shape that we're more familiar with when we look at a telescope. So if you go out to our scopes outside, it's the same thing. They take on a cylinder, there's a mirror inside there, there's a secondary mirror. It's all roughly self-contained within that cylinder. But here it's all out and free. So you have the 6.5 meter primary mirror, that gold-plated mirror. And by the way, that is gold because it has a higher reflectivity. It's the highest reflectivity of the metals you can coat on to coat for a mirror-like surface. So that's why it takes on that gold color. It's just a thin layer of gold. You're not going to send a whole bunch of gold out into space. Then the secondary mirror is just under a meter, about 3/4 of a meter. And just to put that in imperial terms, I guess, 21 feet for the primary mirror. And we have almost 4.5 feet for the, 2.5 feet for the secondary mirror. So that secondary mirror is right up here. So that's the secondary, and this is the primary. And in the end, it functions just like any other telescope. So with our scopes outside, if you're new to Kopernik, I definitely recommend, at the very least, if we don't have something to look at, which we might tonight, but if we don't, then definitely check out the scope so you can look into the interior of the tube. You'll see the primary mirror at the base, and then up towards the top, you'll see the secondary mirror. Same principle. Light comes down on the primary mirror. That mirror is curved, and that curvature collects all that disk of light into a cone. And that actually, James Webb does a great job of displaying that because the struts that hold up the secondary mirror kind of map that out for us. So it contains that cone, and it all focuses down onto the secondary mirror, and that mirror projects it back into the sensor array. So that's the sort of cone-like shape in the center. Now again, for those that are here in person, if you look at just behind you in the back of the room, there is a model of the James Webb mirror that is just about 10th scale. So to give you a little more perspective on that, James Webb is made up of 18 hexagonal panels. And you could fit just about 2 panels on this wall here. So stacked up on this wall, you got 2 panels. Each one of those is almost 4.5 feet in diameter. So again, getting a sense of scale here. This is a big telescope, and a space telescope at that. So we talked about this, the optical telescope element, or the OTE. So then we have a couple of other features we can see in this diagram. We have the Integrated Science Instrument Module. We'll get to that. It's called the ISIM. Again, lots of acronyms. Then we have the Sun Shield. That is a critical part of James Webb. It creates 2 environments around the spacecraft. On one side, this one here, where the spacecraft bus lives, that's going to reach temperatures of 230 degrees Fahrenheit. Extremely hot. On the opposite side, where the mirror lives, this is where the magic happens, that reaches, well, it drops below down to negative 394 degrees Fahrenheit. There's no atmosphere around the spacecraft, so there's not going to be any real sharing of heat, no conduction of heat around it. You're just going to have, or convection, we should say, around the spacecraft. It's just going to be shielded. The mirror is going to be shielded from all that heat, and that's critical. Any heat on the mirror, just like we experience here, if we have unstable conditions, very turbulent atmosphere here, it's not going to be great viewing for us through our telescopes. And for an instrument this precise with this size mirror, you need everything to be as still as possible, because heat is vibration. Thermal energy is vibration. And you need to mitigate that. Drop it down as far as you can go. And that's where this layered sun shield comes in. For those on site, I do invite you to check out the James Webb model in the glass case after tonight's program. That will show you that layering of the sun shield. as well as the mirror on top. That one's 1/100th scale. So again, just get a sense of all the components. Now, at the bottom we have the spacecraft bus, and that's going to house a lot of the operational equipment just to get the telescope moving and pointed at different objects. A lot of spacecraft, a lot of satellite-based spacecraft will have buses like that. So that one's going to be used for your communications, for your electronic and power control. It has star trackers in it. Those star trackers will help. They're little mini telescopes. We kind of use something similar on scopes called autoguiders, and they help us pinpoint objects and target our telescopes and stay on target as well. So a lot of operational equipment in there. Okay, here's another viewpoint. We already talked about some of these things. It's specifying where the star trackers are. Back here we do have a momentum flap, and that's just going to function the same way a trim flap would on a boat or an airplane, except instead of air or water, this is solar pressure. The sun's radiation and particles that it throws off are going to hit this scope and affect its trajectory and alignment. So that momentum flap is there to help maintain its stability. So again, very, very similar to what you'd see on a boat or a plane, but a different current phenomena. All right, let's see, what else haven't we talked about? Spacecraft bus. We have the solar panel, but you can guess what that does. It's going to power all the instrumentation on board and the flight control equipment. The Earth pointing antenna. What's great is that this is close enough that communication time to Earth is only about 1 light second or so. It's not too bad. That means you can almost operate this one-to-one. It's not like operating the Mars rover or the Mars rovers. Those are more like 7 minutes of both back and forth. So just about a light second. Not far enough away to cause too much trouble with communications. And that means your bandwidth is going to be better too, so you can get those photos and that data back down to Earth quicker than a spacecraft that's further out. All right, so we have not talked about the Integrated Science Instrument Module, or the ISIM, and that has a whole bunch of scientific gear in it. That's the laboratory on board. And it's where we get all of these wonderful pictures we're going to see coming up, so I think it's worth talking about. But I'm going to have to use my notes to get these acronyms down. So the first one is the NIRCam, and that's your near-infrared camera. This telescope is an infrared scope, like Spitzer. And again, Spitzer's over there on that blue panel at the top. So it's designed to see that light that's invisible to our eyes. And that's critical for one of its mission directives, which is to look deeper into the universe than ever before. We can talk a little bit about that probably towards the end. So that one's going to be great for cooler red dwarf stars, cooler galaxies out there, and at this wavelength that it looks into, cosmic dust is going to be transparent. So you can look behind invisible light, those clouds would be there. You wouldn't be able to see through them. But with this scope, you can. You can see what's behind those dust clouds, both in our galaxy and in other galaxies. All right, then you have the near-infrared spectrograph. It's going to be looking into the same wavelength of the infrared spectrum, but it's going to, maybe I should pop this next slide on. There we go. So we can see exactly what part of the infrared spectrum it's looking into. This is low energy infrared to mid infrared, and then this is high energy up here, which is what Spitzer was mostly designed to cover. You can see James Webb is mid to high infrared. So that's your spectrograph. That's going to be looking for rainbows. And in particular, these fingerprints that specific light sources give off so that you can identify them. So Every element, every compound is going to have that unique spectra, and spectrographs are designed to pick up that light and analyze it so that we can identify the material that's in a star, a galaxy, an exoplanet. In the news, you may have seen that they are detecting the atmospheres of exoplanets using James Webb, and that's through spectrographs like this, analyzing those worlds and the light given off specifically by the exoplanets. And in fact, that NIRCam that I mentioned before, tied in with this spectrograph, has a coronagraph, and that's designed to block out starlight. So if you're looking at a bright star, but you want to look at the planets in visible light, you want to look at the planets, their dim light that's given off by comparison, then you have to block that starlight out, and that's what a coronagraph is designed to do. It blocks the star so that you can see the dimmer planets around it. So James Webb is imaging planets, exoplanets beyond the Earth. They don't look great in detail, but you get these points of light, and which is a huge step from where we've been. All right, just two more. We have the MIRI, and that's the mid-infrared instrument. So you have your near-infrared here, and then mid-infrared here. This is what MIRI covers in this range. And it's, again, it's the same idea. It's kind of all in one. You got your camera and your spectrograph. And then finally, here's the long one. It's the FGS NIRISS. NIRISS is NIRISS. And that's the fine guidance sensor. That's how it finely tunes its location. And then the near-infrared imager and slitless spectrograph. So that's going to be a couple of other imaging equipment that can be also used for exoplanet detection. All right, so those are the main instruments on board the back of the mirror, where all the sensors are. It gets nice and close to direct capture from what the optics of the scope are picking up. Okay, so let's dive into some images now. So first, starting with objects in our solar system. It has turned its focus onto some planets in our solar system, 4 in total. We're going to look at 2 of them in detail. And in part, it does this to help calibrate the equipment. Of course, we have the best information on bodies that are closest to us, so we can better calibrate the sensors on board James Webb using known quantities, in this case, the outer planets. So we're going to start here with Jupiter. And again, this scope is only 1 million miles from Earth. It's not getting that much closer to Jupiter than the Earth. And this is what it's able to pick up. It's getting comparable to some of the first imagery we got down from Voyager, as far as clarity of clouds and detail. So there's certainly going to be artifacting compared to having a camera right up close, and that's what you see around like these diffraction spikes down here. That's coming from the optics of the scope. So we're going to pick apart what all these things are showing. What's part of Jupiter? What's part of the scope's optics? But this is through that NIRCam, so this is looking near infrared, and we have auroras, rings, moons, and more to look for here. I shouldn't use the laser. I should use my pointer so people on the live stream can see. So here we have the Great Red Spot. Not looking too red, right? In infrared. Well, that is, of course, how NASA's going to pick and choose the colors for the image. That's an important part of how these images are processed in the end. And we'll see that throughout the show. This is seeing in light that's invisible to our eye. So this has to be converted in a sensible way, and even a physically sensible way, so that it makes sense to view in visible light. You're translating it infrared to visible. So it's gonna look. A lot of these pictures are not going to be true to what your eye would see. but they're approximations, and in the end, as far as looking at the image, it's bringing out details that are important for the science behind it. And it just depends on, our brains are processing the colors in this room right now, and this is how we best processed the colors that were detected from NIRCam. So you can see the cloud bands through here. You can see the smaller storms around Jupiter. And if we expand this out a bit, there's more to this image. You start to see some stars in the background surrounding Jupiter. Some of these are not stars, especially those that you see here. First, we have the ring of Jupiter. You may have heard that, yes, Jupiter does have a ring system. It's nowhere near as bright or thick as Saturn's rings, but with infrared light, it's fairly easy to detect, and that's the case for Uranus and Neptune as well. They're thinner rings than Saturn's, more diffuse, but infrared light detects them really well. And Jupiter's is the most diffuse of them all, so this is already doing a really good job. All right, let's bring up some labels here. So we are seeing aurora in this image. Drew was mentioning the aurora, the northern lights we experience here on Earth, and Jupiter also has aurora. In fact, aurora far more powerful than the ones here on Earth. And we're seeing from a telescope far, far away, we're picking up the northern aurora up top and the southern aurora at the bottom. Okay, but there are scope artifacts here, as pointed out in this image. We have diffractions. So you'll see, especially with stars, that James Webb, based on its mirror design, its hexagonal mirror design, it puts off 6 diffraction spikes. And we're starting to see some of those here in this image. So those are the aurora's diffraction here and here and here and here. And then up top, we have the rings. This is Adrastea, one of the moons of Jupiter, one of the smaller moons. Out here is Amalthea. And then way out here, we have another diffraction spike coming into view. And that one's coming from the larger moon, Io. So you can see just how much brighter that's shining compared to the little diffraction spikes coming off of Amalthea. James Webb can resolve the moons of the outer planets, Jupiter and Saturn alike, the larger ones. So that'd be the Galilean moons of Jupiter and the larger moons around Saturn, which we'll get a look at too. All right, so there's Jupiter. Looks a little different from visible light, but a lot of detail. Oh, and also, by the way, the brighter objects in this image are going to be, this is more a measure of altitude. So brighter means higher in altitude, darker means lower in altitude. So there's a lot of high up storms in the Great Red Spot that reach high into the atmosphere of Jupiter, and that's why it looks, why it glows that way. Okay, so Jupiter. Next up, we have Saturn. And you'll notice this is a darker Saturn. Again, it's viewed from that near-infrared camera. We're making out several layers in the ring system. Of course, Saturn is famous for its rings. And we're also starting to see some of those moons. Now, if you remember back to Jupiter, it was still relatively bright. Jupiter is made up of a lot of hydrogen. But Saturn has a fair bit of methane as well. And that methane becomes more prevalent deeper and deeper into the outer solar system, to Uranus and Neptune. But here there is some methane, and methane absorbs sunlight. And in doing so, when we look at it in infrared, we're going to be seeing a darker view So in visible light, it's going to reflect that. But here it's just pure absorption and not as much re-emission in infrared. Okay, so that's our Saturn there, and I got labels for this too. All right, so it's pointing out some of the moons, Dione, Enceladus, and Tethys. One picture I did not include, I believe, is an image. Oh no, sorry, they're going to image Enceladus with James Webb. I don't believe they have yet, but they already have imaged comets and picked up their plumes, and these are comets further away from the sun, where those plumes are harder to detect, and analyzing them. And they're pretty certain that with Enceladus, they'll be able to pick up the geysers that erupt from Enceladus and analyze those. Enceladus is a prime candidate on the search for life in our solar system because it has those geysers, it has it's very geologically active underneath its surface, and it has a liquid water ocean underneath its icy crust. So Enceladus is a prime candidate there. Now, as you look at the rings themselves, it's showing you labeling the C ring, B ring, and A ring. Out here is the F ring. So it's picking up a good portion of the structure there. That gap in the ring is the Cassini division. And that is something we can usually detect in our telescopes. But what's interesting about Saturn right now, a couple of years ago, we were looking more face-on. You'll never look directly face-on at Saturn's rings. But we were looking more at this, if we were to call this the top. We're looking at more of the top. And in doing so, that Cassini division becomes easier to capture all the way around. But with our telescopes here, that's becoming more of a challenge as this ring system starts to go more edge-on. Just like the Earth tilts on its axis, Saturn will do the same. And over time, those rings, it goes through a cycle, and those rings go more edge-on, and then you'll go to the other side and see the bottom, and then back. You'll just cycle through that. And so right now, it's hard to pick up the full Cassini division all the way around. But James Webb really isn't struggling at all. You can see it's picking it up right in here and comes back. Usually, we'll just see these two on either side at this point. So pretty neat that it's picking it up. Now, one of the further out moons of Saturn, and the largest moon of Saturn, it's about, I recall, about 1.5 times, maybe just under that, larger than our moon. So it's appropriately named. It's called Titan. And James Webb imaged Titan. There you go. And again, this is a fairly small world. I mean, for our purposes here, it's the moon, but orbiting around Saturn. And the fact that James Webb is picking up this amount of detail, when the scope itself wasn't necessarily designed for planetary observing, it's pretty incredible what we're viewing here. So this is back in November, and we have a couple different views from the different wavelengths James Webb is able to work with. So in the first one, you're seeing the low atmosphere and clouds. As they say, there's some atmospheric haze, looks like towards the South Pole there, and then we have clouds around the planet, the moon, excuse me. It's hard not to consider Titan as anything but a moon because of how interesting it is. But cloud A, cloud B, those brighter zones on the moon, there they are again in something closer to visible light. They try to approximate. These here are effectively sandy zones on Titan, and that's some evidence for the liquid on its surface as well. There's seas, there's rivers, there's lakes on Titan. It precipitates, it rains on Titan, but it's not water. Titan is so cold that methane and ethane is a liquid at its surface. And because of that, just even at this low resolution, you may say, hang on, that's starting to look a little bit like the Earth, maybe, or at least parts of the Earth. And there's even more detailed imagery captured from Titan from spacecraft like Cassini that have peered through the clouds and looked at its surface. And it is almost, for lack of a better word, hauntingly like the Earth. It's very geologically active, because if you have a liquid cycle on the surface of a body, you're going to have erosion. It's going to carve out your river deltas, your river beds, and even though it's a very cold world, there's still a lot of water on it. A lot of its crust is composed of water ice. And methane and ethane are organic molecules. Now, certainly organic molecules, as we'll see a little bit later, can come from natural sources. In fact, they had to first for us to be here at all. The building blocks of life are organic molecules. But it is a possible sign. You may have seen in the news the past couple days that Mars rover Perseverance detected organic molecules on Mars. Big discovery does not mean there's life there. But it's a start to building up our evidence. So Titan becomes more interesting by the day. And incidentally, there will be a mission launched to Titan at its surface in 2027 called Dragonfly. And that's a little drone that's going to fly around in the atmosphere of Titan. It's a pretty thick atmosphere of nitrogen. So that's something to look forward to there. In 2034, though, it'll get there. So it'll be some little while yet. Just hang around. We'll see you in the next decade. All right. So there's Titan. Now, moving into stars and touching into exoplanets, we'll look at if we have time, we'll look at some of the exoplanet data on NASA's website. But starting with our star here. So this has a great name. It's L1527. And the thing with James Webb is it's so powerful, it's looking at objects that don't have proper names. That's kind of a good thing. Maybe they'll get proper names. And Art back there from our KES is holding up the poster that you can pick up at the tables in the back of the room before you leave. Those came straight from NASA. I believe there's an infographic on the back, too, that will describe the image in more detail. And I'll talk about more of those resources at the end, too. But that is yours to take home with you. So please do. NASA wants you to have them. So this is a protostar. It's hidden from view by cosmic clouds there. You're talking a lot of hydrogen and helium, dust. And dust is just kind of a generic term for all sorts of things, all sorts of molecules that are being generated in this star forming process. And during this star formation, you'll see this hourglass shape start to develop, where this material is jetting out as this star is rapidly churning and spinning up material and starting its stabilized process of nuclear fusion. So this is a very young star, and if you look carefully here, right in the middle, you see this kind of bar shape? So again, we're just seeing some light scattered around that bar shape from the star itself. It's just that stellar reflectance there, and that's what this is down here too. But that bar shape is an edge-on accretion disk. And that is where planets are going to form. We're seeing one of the first steps of stellar evolution here in this image. So our sun was very much like this at one point in its past. We came from an accretion disk just like that. And that's the disk of material that starts developing and where planets will pull together from. So it's pretty incredible image there. And again, just down here, you'll see these diffraction spikes more and more as we look at images with lots of stars in them. They're the sign of brighter objects. Now, what's also crazy about James Webb is that it can't help but pick up galaxies almost no matter what it's looking at, because of that huge mirror it has and that very sensitive equipment on board. So I can't say for certain, but a lot of the fuzzy things in most cases are galaxies. There's a whole citizen science project that takes data just like this and tries to have people categorize galaxies. I can't remember the name now, but I could look it up after the program. And like there's, what is it?
Galaxy Zoo.
Galaxy Zoo, thank you. So if you look up Galaxy Zoo, you could work on that. You could just start picking apart galaxies from all sorts of data sources. But even just looking here, you can see definitely some of these things. Like up here, I'm pretty sure that's some kind of spiral galaxy in the background. Again, it can't help but find them. And that's what it was designed to do. So it's doing well. All right, so again, that poster is yours to pick up in the back after the program. So please do. Protostar. Take one. Oh yeah, there's some more. They were hiding on the other side of the image. Oh yeah, look at this cluster down here. That's a whole. Those are all galaxies there. Those aren't part of our Milky Way. This star is. This is part of our Milky Way, the protostar, not these.
How far away?
The galaxies there?
No, the star.
That I don't know off the top of my head. I don't think I have that one in my notes. Nope, I do not. Sorry about that. But yeah, all sorts of little spirals here. Again, the best way to tell, just generally the best way to tell, something with diffraction spikes is in our galaxy. Something without, that just looks fuzzy, is going to be outside, so a galaxy itself. Oh, here's a cool one. I mean, it's all amazing. But this is Fomalhaut's debris disk. So Fomalhaut is a star, and it's a fairly, if I recall, fairly new star. But you can see the coronagraph there at the center of the image, that little blocking of light. So when you do that, you're not interested in looking at the star at this point. You're blocking that light with a purpose that you can pick up the dimmer material surrounding the star. Sometimes it'll be an exoplanet. In this case, it's asteroid belts and debris disks around the star. So we're looking at the first asteroid belts in infrared beyond our solar system. And this is perhaps the most detailed view of this Fomalhaut system. So I do have some labels, I think, for this one too. Oh, maybe not. Oh, I guess they didn't get added. Well, I can talk to you about it for sure. Let's go back. Nope, we're not going to nebulae yet. There it goes. All right, let's focus in on the image. So we're seeing 3 debris disks in total, and these debris disks would have asteroids within them. So there's the central one right around the star itself. Then we have the intermediate, and then the outer ring. So in our solar system, we have 2 major asteroid belts, the asteroid belt itself, and then the Kuiper belt, which is filled with more icy objects. Asteroid belt is more rocky objects. So we could expect something similar to be playing out here. Now, you may just see, yeah, right in here, there's kind of this brighter area in the outer ring. And at least what they think right now with that outer ring system is it's just a denser part of the rings. It's not indicative of an exoplanet existing there. But yeah, it's I guess possible that after more study, they could determine there's something going on with that denser area of the ring itself. But it would take more observation time to figure that out. Either way, again, you're looking at the stages of belt formation around a star itself. So just James Webb continues to reveal this more aspects of the stellar evolution to us. Okay, now jumping into nebulae. And I want to emphasize, too, there are way more images than this that James Webb has taken a picture of, and I'll give you a glimpse of that when I show you where to find them. These are just some of my highlights, but I'm sure you could find your favorites, too. So nebulae. Nebulae are going to be your star-forming regions. They can also be where stars have died, like planetary nebulae are examples of where actually what our sun will do about 5 billion years in the future. It'll blow off its outer layers. They'll reach deep out into space. And usually they leave behind ring shapes. There's also something like the Dumbbell Nebula. There's a little bit of variety to them. But for the most part, James Webb has been interested in looking at star-forming regions because there's a lot going on that James Webb can pick up. So this is the newest image, Rho Ophiuchi. And it's the closest star-forming region to Earth, observed like never before. So let's just get a good view of it here. And this compressed image that's coming through on the presentation does not even do this justice. You can download huge files directly from NASA's website, or they like to send you, it seems like they're kind of pushing people towards using Flickr now too. So that's an option there. And you can download the originals. And make sure you have a decent computer because with good RAM, because they're huge files, but so worth exploring. You can spend all day zooming in around this image at this crisp detail in these hydrogen lanes here. So this red is ionized hydrogen. You can see all these kind of bubble shapes around these early stars. When Drew and I were looking at this image the other day, he noticed that these are double stars here and down here. You see how there's multiple diffraction spikes if you look carefully. They double up, and that's because there's two stars there, both at the top and bottom. So again, very much like something we'd be used to around our area, the Orion Nebula. That's the stellar factory that we get to see every year, and you can see parts of it with just your eye. It's a nice bright one. This is very similar to that. And one more thing you may notice with these protostars, you see these hourglass shapes again. That's commonplace. That's just the nature, again, of stellar evolution. You'll get that material thrown off as that star ignites and churns up that material around it. You'll get that jetting from the poles of the star. All right, so yeah, just a brilliant image. And maybe I'll use this one as an example of just, assuming this computer can handle it, we'll see. We'll zoom in and explore a little. So Rho Ophiuchi. Okay. Here's another neat one. This one did not have a proper name when I was looking at it. The official title of it is the Prestellar Ice Chemistry. And in it, we're seeing evidence for frozen carbon dioxide, ammonia, and methane. Again, these are precursors to the building blocks of life. So it's a nebulous region in space. You have these ice crystals forming of these organic compounds. So if you've seen dry ice before, that's the kind of stuff we're talking about here. That solid, those solid organic molecules. And what's also neat about this is there's some evidence that this region of space is forming those organic molecules beyond star formation, which is fascinating. If that's the case, it does, again, more study needs to be done on this, but it does start to make us ask, are there pathways beyond just this stellar evolution that brings us to these organic molecules that, in the end, potentially will lead to life somewhere in the universe? It's a fascinating concept, and if we see the whole image here, there you go. So these are these ice clouds, this nebulous region. And it does certainly look like there is some stellar formation activity going on in this zone. And this one does a good job of showing you that artifacting, too, on those diffraction spikes. I will say sometimes those can be a little distracting. Around the brighter objects, there can be a lot of them going on, but it's just the nature of the scope's design. It's still picking up a lot of crisp detail, but you will see those diffraction spikes everywhere. Okay, galaxies. And I don't think just that seems lacking to me. I think that's better. So there, like I said, James Webb can't help but pick up galaxies wherever it looks, unless it's the core of the Milky Way, where you're just not going to really penetrate through that dense area of our galaxy. You're gonna pick them up, and that's brilliant. So let's take a look at some of them. I say some. This is Pandora's cluster, and it's assembled from 4 snapshots. So this is a mosaic from the widest field of view of James Webb, and it depicts 3 galactic clusters merging into a supercluster. So let's look at this in more detail. So you see all these fuzzy zones here. Those are going to be depicting the 3 clusters. So we have one here, and one up here. And these are merging. Now, we don't see this nearby our galaxy. The universe is presently not as dense as that. We're looking back in time, billions of years ago, when we look at images like this. In the early stages of the universe, or I guess these brighter ones here are going to be maybe half that, 5 billion years ago. And then looking even deeper and deeper, all these red, darker red objects. Here's a little one up here. Those are indicating the oldest galaxies in our universe. So approaching 13 billion years old. At a certain point, at least after the Big Bang, several million years after it, the universe was opaque. So we can't look through to that, even with something like James Webb. But we can look just after. Once the universe becomes transparent, we can see those first galaxies. And that's what James Webb is designed to pick up, the earliest galaxies in the universe. So yeah, if I recall, we're looking somewhere around 50,000, they say objects in this image, because there are some Milky Way stars in here. Anything, again, with a diffraction spike is going to be a star in our galaxy. And because it just takes time to analyze this, you can't be certain every single thing, every single fuzz is a galaxy itself. So right now they're saying 50,000 objects in this one. Want to start counting? Just this picture is very similar to the Hubble deep field or ultra deep field. And the thing about James Webb is that every dark spot it looks, where you're not looking through thicker parts of our galaxy, you're just going to be seeing things like this all the time. Also, you'll notice, especially around these clusters, notice the warping of the galaxies in the background. That is gravitational lensing. It's something we've seen a lot of with this scope and others. It's exactly what it sounds like. It's an optical effect generated by large gravitational sources like superclusters. So we're looking, in a lot of cases, at galaxies behind the supercluster, which is neat, because if that wasn't a physical phenomena that occurred, they'd be obscured. But because of all that gravity in place, we get to look behind the object, the primary objects here. So all these little curvy, warpy galaxies, look, see how this one's stretched. That's the gravitational lensing in action. All right, so this one's going to be a video. And this is called SEERS. Again, nice acronym. Cosmic Evolution Early Release Science Survey. I'm going to pause it for just a moment. If I can. There we go. So, again, Cosmic Evolution Early Release Science Survey. And we're going to see 5,000 galaxies here. We're going to fly through them as if you were in a way faster than light speed spacecraft. And we're going to end, it says flight to Maisie's galaxy. We're going to end with this galaxy called Maisie's. And it's going to be one of the oldest galaxies ever detected. Again, we're talking 13.4 billion light years away. So one of the first galaxies in the universe. So let's fly through. And this data was captured from James Webb. So let's just get back to Maisie's there. Good. There we go. Oh, it's not going to let me. Ah, it doesn't want to click back. Oh, wait, there it goes. Let's try it. Oh, this is not fun. There it goes. Oh, it did. Well, maybe we won't get to see Maisie's one more time. The media player doesn't want to work. But yeah, that little fuzz of red is at least the first infrared light we're seeing of the universe. Now, what's interesting about that is that when we look at galaxies out in space, certainly like James Webb does, all these galaxies here are detected in near infrared and mid-infrared light. But that galaxy would be outputting visible light. And technically, that is what they're detecting. But because that galaxy is redshifted from just the universe expanding, it shifts the spectrum of that galaxy. And that's also how we're able to measure how far away it is, because we know what a galaxy should be made up of. You'll find a lot of hydrogen in it from the stars and the nebulae within. And you're going to look for those spectral lines in your spectrometer, and you'll see them, but shifted into infrared rather than visible light. And that's how they're able to measure the distance to that galaxy at 13.4 billion light years away. So pretty fascinating. And there's this again might be a little compressed, so give this a download at home too, or watch it on YouTube and enjoy. It's a really nice video they made. Okay. No, we want to go ahead. Here, let's do this. There we go. So getting into NASA resources now. This is just a couple of slides. First, I just want to detail what we have to hand out to you tonight. Again, you can pick these up on the back table. First, there's that image, that poster of L1527, that protostar. It's a very nice quality print with some information on the back, so feel free to take that home. There is a Pillars of Creation bookmark. That was one picture we didn't have in this clip. It did come out maybe late summer, early fall in 2022, was that when the James Webb image of Pillars of Creation was revealed. This is also the Eagle Nebula. And there's some neat comparisons you can look up of this James Webb infrared view versus the Hubble image. It's looking through a lot of these dust clouds. You are looking behind these pillars now. And so that's the bookmark. And then finally, there's a sticker of one of the James Webb logos. And I really like this one because it just has this nice graphic, and it stretches deep into deep space looking at those earliest galaxies out here. So those are all for you to take home. And of course, if you want to learn more, you can go to nasa.gov. In fact, let's quickly just jump to that so I can show you where to go. So among the best ways to navigate to all these images is to just jump right to nasa.gov, go to Missions, James Webb Space Telescope, then go over to Images. It'll also give you some current events happening with James Webb, so it's a nice page to follow up. There's also I think it's webtelescope.org, which is kind of the collective for all agencies, because this isn't just NASA, right? It's NASA, ESA, and CSA. So it's where all the science goes to. So you can visit webtelescope.org. And let's see. Yeah, so this takes you to the latest images slideshow, and you can click through. I know there's a lot of, because they celebrated the 1 year of science on Wednesday, people were making all sorts of neat models and imagery. Oh, that's an interesting one. So if you just click down on this, it'll take you to the Flickr page. And you can just follow this if you have Flickr and stay up to date. There's an albums section, which has web images from 2023, from 2022. Here's the row of Fuji. If you just click on that, you can download the original file and look at that pixel count. It's about almost 13,000 by 12,000 pixels. So let me just show you what that means. Again, I hope the computer doesn't die on us here. Let's see if it'll load it all right. So again, you can, with a picture at this scale, you can just dive deep into this crisp data collected. There's that protostar we were looking at before. Yeah, I did before. Yep. In fact, let's go over. So you can really see those much clearer now, where the lines are doubled up, right? And the diffraction spikes are different colors too. Another indication for those two stars being there. I think there's another double star down here, right? Yep. There's the second one. And yeah, I can't get over just how crisp the hydrogen detail is in this image. I mean, in a way, it just makes all these images with hydrogen like this will just make you think flames or fire coming off the nebula. That's not exactly what's going on, but it really does show up that way in this frame. So you could spend hours looking through these at their max detail. Let's go back one more time, and I'll just quickly scroll through. This is just what they got in 2023. So you'll find some of the images are, especially for the dimmer objects and fainter ones, where there's not a ton to look at. This is a galaxy, an early galaxy, 12.7 billion light years away. And that's real light that can be picked up by a spectrograph. And in doing so, you can figure out what that galaxy is made from, or made up of. So you got your hydrogen, your oxygen, your iron. You're getting heavier elements at this point in the universe forming in those galaxies. And what they're finding is galactic formation kicked off a lot sooner and stabilized a lot sooner in the early universe. So there's some galactic clusters there. I think this is part of, the Orion bar. Yep. And this, again, is just 2023. There's a Fomalhaut. There's Uranus. We didn't have that in the slideshow, but that's another nice one. You can really see how those rings pop out. There's some really nice gravitational lensing around that cluster there. Again, you could, of course, do this on your own time. This is an accretion disk. Again, there's that coronagraph that's blocking out the starlight, so you can make out this thin bit of material around it that's forming planets. And there's the data collected for 2023. So, I definitely invite you to jump on that and take some time to. Oh, the Flickr page or NASA? NASA. Let's go. So I've done enough. I don't know if backing up would get us there. So let's just jump right back to it here. This one?
Yeah. How did you start with the images?
Oh, so you just go at the web homepage. You just go right to images.
Scroll down a little bit. Next one down.
Yep. This one here?
Okay, I just wanted to see.
Oh, yeah. Yep. So this is when it was under assembly, at least at Northrop Grumman. Yep, no problem. So I only have one more slide now. So any questions to close out the show? Do we want to?
We do have some on the chat, and I apologize. I had to step out for a few minutes, and so if you answered one of these questions, just tell me so.
Okay, yeah, no problem.
I think it's called Floaty. The question is, have they already, or do they plan to repeat photographing the area of the Hubble Deep Field image?
Yes, they're slowly collecting data from Hubble Deep Field, and will continue to assemble a similar mosaic. Similar, a better mosaic than Hubble Deep Field. You'll continue to see data collected for that, and eventually, I'm not sure what their timeline is for their final image assembly, but they are going to continue capturing that zone of the sky. Yep.
Next question, also from Floaty. What is the anticipated functional lifespan of James Webb?
Oh, yeah, good question. So initially, they were hoping for maybe 10 years out of it. But from what they've said, the flight to that Lagrange point was so streamlined that they conserved a ton of fuel. And as far as fuel is concerned, their estimates go to 20 years. It could even go a little beyond that too. But of course, that does not account for unexpected events like meteor impacts. And James Webb already has had one of its panels hit by a micrometeoroid. Now, thankfully, the mirror is designed to be as large as it is to mitigate some of those impacts. But at a certain point, they would start affecting the mirror if enough of them happened. Now, the real unfortunate thing is that happened so soon after launch, and during calibration, they detected that. So it was almost a little disheartening at first, but it's still overperforming from what they planned on. So even with that impact happening. But if more were to happen, the lifespan will deteriorate. So some of it's unpredictable, but as far as fuel goes, about 20 years.
And our good friend Captain Longboarder asks, how many gyroscopes are there? Are you aware?
Oh, that I don't know. That'd be in the spacecraft bus, but I'm not sure how many they have inside.
All right. We'll just do another quick check here. Any other questions here in the main audience?
Got one.
Oh, here we go.
Were you saying that it takes a second to get light back and forth to the Webb telescope?
Yeah, that's what they estimated on the stream the other day. But
I mean, if my math says that light travels at 180,000 miles a second, and that's a million miles away. That's about 5.4 seconds.
yeah, that might be closer. I mean, they may have just been a little wishy-washy with their estimation.
A little blib.
Yeah, but either way, I guess because when you think about it, I guess the moon is maybe 3 seconds or so, thereabouts.
Well, one way would be a little more than a second.
Right, so 3, right, there and back. So yeah, that adds up. It might be a little over. But either way, still low latency by Martian comparisons, for example.
Any
Thank
other
you.
questions here in the room? Otherwise, because I know we've got a few more on the chat. So sneak back in here. And actually here we'll illuminate Jeremy. Let's see here. There was a question asked, are Cloud A and Cloud B around Titan's clouds as we know them? Are they clouds as we know them? Because they seem fixed and permanent.
So there are, in fact, much like Venus, Titan is almost entirely clouded. Now, those clouds there, I'm not sure if you capture data over time or not, if they do appear fixed. But at least from my observation there, they would potentially be brighter and denser areas of the cloud coverage on Titan. But yeah, if you were on the surface of Titan, you wouldn't be able to look through those, through up into the starry skies or see Saturn even. It's clouds all the time on Titan. And yeah, I'm not entirely certain of the nature of those two in particular they had highlighted there.
All right. And finally, there was a comment from Fred. This is, I believe, JWST did observe a mega plume of water vapor on the southern pole of Enceladus in June, and it was measured to be something like 6,000 miles long.
Oh, okay. Maybe it did observe Enceladus then. Yeah, I didn't find the data, but I'll have to check that one out.
All right. Any other questions? I don't see anything else in the chat. Again, one of the things we do here at Kopernik is we have a rule that says you can't leave Kopernik until you look through a telescope. Unfortunately, you're going to be waiting a long time. It's pretty clouded over, I believe. So no. Oh, I take that back. All right. So we will open up some telescope domes, and again, the rule here is you can't leave till you look through a scope. So. If you head through the lobby, there's another set of double doors, and then the observatory is on the left, and Alan's binoculars are just straight ahead. So thanks again, Jeremy, for outstanding presentation. And next Friday night, our program is the Great Telescope Dust-Off. If you've got a scope at home, either in the attic or basement or in your garage that's collecting dust and you haven't used it in a while, bring it up. We'll check it out and show you how to use it. Thanks.